Hello and welcome to our presentation on quantum combinatorial design. Today I'll just go and quickly give you a brief overview of combinatorial design, the difference between classical and quantum computing and how it fundamentally changes the way that we might solve our combinatorial design problem. We'll present the results of a 2D tiling problem that we have been trying to solve through quantum computing means, and then end on some concluding remarks and key features of quantum computing and what we might need to solve and rethink how we solve our design problems. So combinatorial design is a well-known problem in engineering design. We typically see it in terms of layouts, optimizing layouts of manufacturing facilities, the optimization of mechanisms, joints and pins to get a desired motion for our products, and tool pathing in the manufacturing scene, where we want to optimize the manufacturing process. So how we might solve those, typically in a classical realm, well, they are built of those combinatorial problems are built of a set of parameters and constraints, and then we would typically iterate through those design options and evaluate against our criteria to say if they're valid or invalid design options for a design problem. There may also be an objective function where you might want to then assess its performance for a desired characteristic. But simply, like say classically, we would then iterate through. So here's a simple case where we've got 3 blocks where we're just iterating through the potential solutions of how they might be joined together. But quantum presents a whole new opportunity to represent the design problem in a way that actually in the quantum realm, we can represent all the design options in one ensemble, one instance. So here we've got this just illustrative example where we're creating all of those solutions in one instance in the quantum realm. The challenge with quantum computing is that when you measure a quantum computer, then you return a single solution from your solution set. So what we've been investigating is how we can manipulate that quantum realm to represent our constraints and only the valid solutions, and then use it to then return the valid solutions through measurement. So here we have had a 2D tiling problem. So again, we're very, very early stages. It's a 2x2 grid with a blue and red tile. And we've been looking at how how we position and create all the design options for a 2D tiling problem. We have then looked at how we might add constraints such as no overlap, no 1-1, which is a no placement in a particular area of that design space, and how those constraints might combine and the challenges in combining those constraints. So in summary, the results show that, really promising that we have the ability to represent our design options in a quantum realm. We have shown that by adding constraints, we can reduce the design space to only the valid solutions using our quantum circuits. In doing so, we shift the measurement probabilities, and that's something of an interesting feature and a particular feature of quantum computing, that no information is lost. Therefore, we need to be wary that what we're doing is actually shifting the measurement probabilities of valid solutions up, and how we might want to do that, equally is of a continued challenge. And we've also identified that combining constraints is a non-trivial task. So you can't simply just append quantum circuits for particular constraints and feel that they won't interplay. They do, and they do have an effect, so they can reintroduce invalid results to the solution set if we don't configure it appropriately. So just some quick concluding remarks then. Yeah, quantum computing provides a really exciting and new way of modeling design spaces. The tools are emerging now that we are able to, help us as a discipline to use and investigate quantum computing using such as the IBM quantum experience and Python toolboxes such as Qiskit. The challenges going forward is how one can score solutions against an objective function, how we manage those measurement probabilities and assist manipulate them to maybe promote ones that meet our objectives to a greater degree, how we manage the bias introduced into our constraints, so we do not just bias a particular solution in our design space, how the quantum circuits scale with size, and maybe how we might use quantum computing to just describe the topology of the design space, not actually just pick out particular solutions. Ultimately driving towards this idea of what are the guidelines, support, and design process for constructing combinatorial design problems. So thank you for listening. For more on the subject, please see some more of our papers or contact me. We're really excited to bring this new technology to the engineering design community and to develop it further. Thank you very much.